totalmente reactivado. Okay, can you hear us? Yes. Can you hear us? Yes. Okay. Okay, let's start. So sorry for the multiple technical problems that we have today. We tested it yesterday, it was perfectly working. But of course, it's the first seminar of the year and things happen. So today the speaker is Borja. Borja is doing his PhD in Granada with Enrique Pérez Montero and Pepe Vilche. And he's visiting us this week, so he will be all the week in the student room. And he's from Gijón, from Asturias. That's where he studied. Well, he moved to Oviedo to study physics and mathematics.
I still stay in
You didn't really move.
Yeah, not at all.
And then from there, he moved to Granada to do the master in astrophysics and to start the PhD. And today, he's going to talk us about the chemical abundances in AGN measured with optical and infrared fine structure lines. So thank you very much, Borja.
Thank you.
All yours. I hope it doesn't explode.
Let's hope we keep it for the hour. First of all, thank you for inviting me to stay here this week. I have never been in Teruel before, and it's really nice. It's a small city, so you can have everything in hand, and it's so beautiful to walk around even in the night. It's so pretty, the city. So today I will present you the work that I've been doing these 2 years, mainly from my master thesis project and also from the first years of my PhD, which is analyzing the chemical content of the Nebular region, but also for the gas in star-forming galaxies. This work has been done in collaboration with many people at the IAA, but also in collaboration with Juan Antonio here from CERTA. So the outline of my talk, first of all, I will introduce you some details and a brief summary of how can we estimate the chemical content of the gas in galaxies. Then I will explain our methodology, and this is going to be the marketing part of the talk. I'm gonna sell you our technique, and I want you to apply it if you can. Then I will show you the main results that we obtained from optical emission lines. Secondly, the main result that we obtained from infrared emission lines, and how these two studies can lead us to many lines of work that I will show you in the next steps. And finally, I will leave you with some remarks, some takeaway messages, especially the one of buying my methodology, our methodology. This is the one that if you keep it in mind, it will do it for me. So let's start. Let's assume that we observe spectroscopically the nuclear region of a galaxy. There we have, in the one hand, the stellar emission population from that center, but also if we remove that, if we modelize that, there are many techniques now in the market that can allow you to do that in different types of spectroscopic observations. Then in some galaxies, we still receive some emission characterized by strong emission lines or weak emission lines. And this emission can only be explained due to the star formation in the center of the galaxy or AEN activity. In both cases, we are ionizing gas, and that gas is emitting us those emission lines. In the case of star formation, the main source of ionization are really hot massive stars, OB stars, that are ionizing a gas characterized by 10 to the 4 Kelvin, densities of 100, even 1000, and small velocities, 10 kilometers per second. On the other hand, when we talk about AEN, we are talking about a supermassive black hole, which has an accretion disk surrounding the supermassive black hole, and that accretion disk, due to the temperature, is emitting ionizing the gas. We found gas in 2 different regions. One region really close, oh no, I will change to, well, I will leave it with the last one. One region which is located really close to the supermassive black hole, and therefore it has higher velocities. The density is also higher, although the temperature is quite the same. But due to the density, we only see here recombination emission lines. On the other hand, we have a region located far away, which is the narrow line region, which is the one that my talk is going to be about. And this region has really similar characteristics to that gas that we observe in star-forming galaxies. Although there are some discrepancies, for instance, in the density. We expect to have higher density in these regions than in star-forming regions. So these are the two main sources of ionization that we found in the center of galaxies. And we need to account for these two different sources. But why metals? Well, metals, as you know, the nucleosynthesis Big Bang only produces hydrogen and the most part of the helium that we observe. Also, really small traces of lithium. All the rest of the metals, well, you know that we astrophysicists we call just metals, everything higher than helium. It's easier to remember that. Every single one of the metals are produced by stellar nucleosynthesis, up to the iron. The nucleosynthesis in stars allow us to produce those metals that later, on the latest stages of evolution of these stars, are ejected into the interstellar medium via winds, via different kind of movements of gas that allow those metals to be thrown into the ISM. And how can we estimate these metals in the concept of galaxies? We mainly use two traces. First of all, the oxygen content. Why oxygen? First of all, it's the most abundant metal in mass that we found in the ISM. And secondly, it's precisely to prominent emission lines that we detect in the ultraviolet, in the optical, and the infrared range. So it's kind of the thing that we need to look for too. On the other hand, we have the nitrogen over oxygen ratio, which is not so well, let's say, studied in the literature, because many people just assume a relation between these two quantities. So yeah, we can use nitrogen emission lines in order to estimate the oxygen content. That's my second takeaway message is don't do that, please. And this chemical ratio, it's really important, as I will show you later, because it allows us to somehow estimate the evolutionary stage of the metals in the ISM. But how can we measure these quantities, or at least how can we estimate these quantities? Well, we have three main techniques. First of all, we can apply the diode method. In other words, we know every of the physical conditions of the ISM, so we apply the theory of emissivity and then we retrieve the chemical abundances. It's just solving equations. What's the problem? Once we move to the infrared range, many of the emission lines, its emissivity doesn't depend at all on the effective temperature. In other words, the electronic temperature, sorry. In other words, it's extremely difficult to estimate the electronic temperature in the infrared regime. So that technique can be applied indeed for oxygen, for the optical regime, although those emission lines that are strongly dependent on the temperature, also called aurora lines, are extremely faint in many cases. However, we can just apply photoionization models. We know that in both cases, AGNs and star-forming regions, the photoionization is the main driver of the ionization of the gas. So we can just modelize that, accounting for the AGN or for OD stars, and then in those photoionization models, we introduce as inputs the physical conditions and the chemical conditions of the gas. Therefore, we can infer the chemical conditions. And lastly, we can use calibrations. We just use emission line ratios, which are known to be correlated with the chemical abundances, mainly because of the two above studies. Either by applying the direct method of photoionization models, we can search for calibrations for different emission line ratios that are sensitive to these chemical quantities. As I told you before, nitrogen over oxygen is really important. And this is the reason. Oxygen is a primary element. It only forms in massive stars. But nitrogen is a secondary element. This means that while nitrogen and oxygen can be produced by massive stars, if there is enough oxygen in the gas when the star is forming, for intermediate mass stars, CNO cycles can be enhanced, and then we have another channel of production for nitrogen, which is the scaling relation that we see in this part. For high metallicity regimes, we expect that nitrogen is also produced in a secondary channel. So we have additionally another source of nitrogen. In other words, we are analyzing the evolutionary stage of the metals, if are already present of the gas or not. And then Then the studies. Why aliens? Well, as I can show you here, these are just a small fraction of the whole literature that you can find on star-forming galaxies and the analysis of the chemical content of the gas. On this hand, they are also scarce, but we also have studies for AENs. The problem is if we move to what is called low luminosity AENs, which are regions with the least power source because of the inefficient accretion rate that we expect for these systems. And then let's take a look of if optical, ultraviolet, or infrared emission lines are used. As you can see, only in recent years, infrared emission lines are starting to be applied for AEMs, although this study seems to be also performed in star-forming galaxies. Only in low luminosity AEMs, my work for last year, is considering these sources to analyze. And there is clearly lack of ultraviolet estimations for these kind of sources. So this is an ongoing work that needs to be keep doing in order to just infer the same properties or check if the same properties that have been studied in star-forming galaxies from mostly early 70s are found in AENs or not. Because this allows us to understand if AENs are also displacing these galaxies from the standard, let's say standard way of evolution. Why they are tracing galactic evolution? Well, it has been known for many years that the stellar mass correlates with the metallicity. Even more, we can complex this scheme and we can also search for the star formation rate, the efficiency in forming stars for the galaxy. And we also found that there is a correlation, which is the fundamental plane. Why this is so hard? Because there are many reasons. So maybe we have driving outflows that are carrying this metal content. We also can infer that high mass galaxies are in a different evolutionary stage. Also, for metal poor systems, it seems to believe, and it has been detected, just in really few cases, that there are inflows of metal poor gas. There are many, many ways, and here I show you just 5 of the reasons with many examples of these papers where they detail how these processes can be occurring. But if you want a quick review, and in my opinion, an excellent one, because you have all the sources there, just check for Majolino Manucci review from 2019. It's really nice. But yeah, I mean, stellar mass, star formation rate, indeed, it is inferring that the chemical content is related to the galaxy evolution, how the galaxy is forming stars and the efficiency in that. Also, we can see that, although this study doesn't show clearly this correlation, there is a gradient in metals when we search for that in galaxies. Why is so? Because gas is driving into the center of the galaxy via secular evolution, and hence these large amounts of gas that are located in the center enhance star formation. If you have enhanced star formation, you expect to have higher metallicities in that center of the galaxies. So this is also a well-known result that has been also tested nowadays with IFUs. What about AENs? Those results are for star-forming galaxies. What about AENs? Well, AENs, some authors claim that indeed we can see that we have the evolutionary track from the mass metallicity relation, and in the end, we have those AENs kind of merging and following the relation that we infer from star-forming galaxies. Also, significantly, we can see that most of the AENs here and also here have higher abundances than those expected for star-forming galaxies. Many authors claim that that could be possible due to dust destruction, not only the narrow region, but between the broader region and the narrow region, we have a region of dust, which is the torus surrounding the supermassive black hole, that can be destroyed in some cases due to the radiation field that can be enhanced somehow because of changing AEM, something like that. So that dust that has been destroyed will be accreting metals into the gas, therefore enhancing the appearances. Also, AGN-driven outflows, as I told you, supernova-driven outflows can explain why metals in massive galaxies are so high. Indeed, we have also AGN-driven outflows that could explain these high metallicities. So this is the state of the art. And what are we going to present you? Then our methodology. A methodology that can be applied for both star-forming galaxies and AENs. And instead, as I told you before, there are 3 main techniques: the direct method, potentiation models, constraining calibrations. This technique, which has been developed by my PhD supervisor, Enrique Pérez Montero, takes advantages of two of those techniques. The second one, potentiation models, But instead of matching single emission line ratios, which is the calibrated models that many people use in the literature, we search for calibrations. In other words, we search for emission line ratios that are sensitive to these parameters in order to efficiently constrain the grid of models that we present to infer these chemical properties. Not also the chemical properties, the oxygen and the nitrogen over oxygen abundance ratios, but also the ionization parameter, the strength of the field that is ionizing the gas. Here, I show you a summary of our grid of models. And this is the first time that Linus has considered. That's our main. That's the main point of my work that I will present you in this talk. And as you can see, we account for the differences that I told you before in the introduction between star-forming regions and regions. In star-forming regions, we have the stellar population ongoing formation because of the enhanced presence of the gas, while in AGNs we have modelized the emission by a power law, the classical power law with two slopes and the big blue gamma. So not only we account for these differences, but also in the case of AGNs, we account for the differences in their strength. As I told you before, liners have inefficient acquisition rates, and therefore the strength of the field, of the ionizing field, is less powerful than in the case of CIFERs or type 2 AGNs. Therefore, we account for these differences by constraining the grid of models. This allows us to perform a more efficient determination of these chemical abundances because there is some degeneracy in the problem, as we try to estimate three quantities, two chemical abundances ratios, and the ionization parameter with some emission lines. Which emission lines? Here I show you the main input that you can introduce in the optical version of our code. Just these few emission lines, and there, what our code does is that by a bayesian-like methodology, we constrain the grid of models. First of all, we constrain the nitrogen over oxygen ratio, and then in a second and third iteration, we constrain the oxygen and the ionization parameters. In the case of the infrared range, the methodology is the same. What is changing is the input lines that we need to introduce. Here I show you the list of emission lines that we can introduce. We are now upgrading the code in order to take into account for the many features and emission lines that can be found in the new data from the James Webb, which is amazing. So this list will be increased quite a lot, but we have one problem right now. And the problem are the far infrared emission lines. These emission lines are key to estimate in the infrared range the nitrogen over oxygen ratio, which, as I told you before, will allow us to understand the evolutionary states of the metals. Sadly, Sophia has been cancelled, so right now our only possibility is for high-aggressive galaxies to estimate these lines from ALMA, but in the nearby galaxy, in the nearby universe, sorry, we cannot do anything. Sadly, if somehow we have just a really strange galaxy measured with James Webb and we want to see, wow, how is the nitrogen oxygen ratio behaving? Well, just cross your fingers, search in Sophia archive, and if not, well, wait with me for 10 years or so in order to see another far infrared observatory ongoing. So the main results from optical emission lines. What do we use for this study? The Palomar spectroscopic survey. It's a really well-known survey published by Ho et al. In middle of the 90s. And essentially, we use this sample because we have lots of information from the host galaxies in the sample. And we started a filtering process. Already, the original sample is up to 486 galaxies, but then we need galaxies showing clear nuclear emission lines. Indeed, there is a star formation or AGN activity ongoing. Then we discard broad lines. The main reason is that broad lines, as I told you before, can only be originated on the broad line region. And therefore, we do not see the emission from the broad line from collisional circle lines, emission lines, for instance, for oxygen. Therefore, if we measure hydrogen emission lines, recombination lines, we will be adding the emission from the broad line region. In other words, we will be diluting the intrinsic emission from the narrow line region. Therefore, if we remove that contribution, we will be only calculating from emission lines coming from the narrow line region. And then we also add let's say a quality filter, which is of the measurement of the emission lines in order to retrieve accuracy measurements of the chemical abundances. What we obtain, first of all, we classify the sample. Also, how provided the classification was made in a really primitive way of the DPT diagram with just horizontal and vertical lines. And here we introduce the criteria by QLI in order to classify our sample of galaxies. And as you can see here, we have a huge sample of star-forming galaxies. Then we have mainly liners, low luminosity AENs, because low luminosity AENs are the most abundant AENs in the nearby universe. So they need to be analyzed indeed in order to check why the AENs in this, let's say, in this moment of the universe are behaving like that. And then we have a small fraction of CIFERs too. Why do we keep analyzing star-forming galaxies when we are interested in an NLR region? In order to check the robustness of our methodology. If we found the same relation in star-forming galaxies applying the same methodology, then our results from for AENs, if they deviate or not, can be in some way contrast because we are able to reproduce both behaviors. So what are we obtaining? First of all, for star-forming galaxies, as we are using the Palomar spectroscopic survey for really nearby galaxies, we are focusing on the nuclear region of those galaxies. And as you know, there is a metallicity gradient, so we expect higher metallicities in these galaxies, which is the thing that we found here. Most of our galaxies belong to the regime where the nitrogen is already producing a secondary channel. Why? If we take a look at CIFERs or even liners, we do not see a correlation at all. And it's why it's important to estimate nitrogen over oxygen first. Because if we just assume that the nitrogen over oxygen ratio behaves in the same way as in star-forming galaxies, then we will introduce a strong bias. And as you can see here, there is no such a correlation. Indeed, other studies show that that correlation is not found at all, even for the ionization parameter. So the problem is that we cannot infer the same properties that are found for star-forming galaxies for samples of AENs. And this is an issue that is not so well addressed in the literature because many people just assume that the nitrogen over oxygen is behaving in the same way for all galaxies. AENs are expected to have higher metallicities. Therefore, we are in the branch where nitrogen is already produced by a secondary channel, and therefore we assume the scaling relation. And as I told you before, not at all. We are able to reproduce that scaling relation in star-forming galaxies, but we cannot reproduce that neither in CIFERs, although the sample is small, okay, but in liners neither too. There is no such a relation. And if you're assuming that this nitrogen over oxygen ratio belongs to what is supposed to be the scaling relation, you will be underestimating the oxygen abundance or underestimating it. What about the properties of the galaxy? As I told you before, the Palomar spectroscopic survey has ancillary data on the properties of the host galaxies. So now we can check for relations in the chemical abundances and in the host galaxy parameters. The first one, the so well-known stellar mass. Are we able to reproduce the stellar mass metallicity relation? Indeed. The main problem again is that we are focusing on the nuclear region of these galaxies. Therefore, we are in the branch, in the plateau of the curve, because we are just measuring chemical abundances in the real center of those galaxies. However, what about AEMs? Well, in AEMs, it seems kind of like CIFERs can behave producing the mass metallicity relation. Also, there are some layers here, but what the picture that liners, low luminosity AEMs are telling us is that no, they are not following the same relation. So, to those 5 mechanisms, driving outflows, the different evolutionary stages of the galaxies, there is some factor to be account for AEN activity. As we can see, AEN activity deviates these galaxies from the standard behavior in the mass metallicity relation. So we decided to check for other biases, morphology. Maybe morphology is somehow introducing a bias in the metallicity, and therefore we can explain why these AENs, why the host galaxy AENs, then its mass does not correlate with the metallicities. But what we can see is that morphology only introduces slight changes, but for irregular galaxies. And this is not due to essentially morphology, it's due to mass. These dwarf galaxies have less stellar mass than the others. So this behavior is again the mass metallicity relation. What about H-alpha luminosity? The H-alpha luminosity is somehow tracing, it's tracing mostly in star-forming galaxies the star formation rate, the star formation efficiency. And as we can see, we're reproducing in the behavior. which is the fundamental plane that I showed you before in a 3D diagram, but here we just slide it in the two different dimensions. However, there is no such a correlation with AENs. So we kind of think in a property characteristic of AENs that would allow us to understand if there is indeed some correlation with that property and the chemical content, which is the mass of the supermassive black hole. The mass of the supermassive black hole mostly dominates all the properties of the AEN, its efficiency, its luminosity, its evolutionary states. So we estimate the mass of the supermassive black hole by measuring the dispersion velocity of the stars in the center of those galaxies, but we obtain so far that there is indeed no correlation at all. So it seems that the chemical abundances in AENs doesn't correlate at all with any of the properties that we think maybe you have a suggestion. So I will be open to that and I'm glad we discuss it. But so far, all the properties that we analyze doesn't correlate at all with the chemical abundances that we obtain. So now let's move to infrared. Why infrared now? Well, first of all, we obtain somehow some shocking results by analyzing optical emission lines. It seems that in AENs, we do not find a correlation at all with the chemical content. So we decided to check infrared emission lines, and in light of the James Webb data that will be obtaining in the next years, would be really amazing if we can check again these results, but via infrared emission lines. First of all, here I show you like the promotional slide. We have already ancillary data from Sophia, Spitzer, Herschel, etc. But the new data that will be coming will enhance the information that we have for the infrared range, especially for the spectroscopic information. There are so many studies that have been performing, as I showed you before in that slide, already for emission lines, for estimation of chemical abundances from infrared emission lines. Here I show you the work from a really unknown author, Juan Antonio, which also participates in the upgrade of the HII-CHI-MISTRY, the code that I presented you before, to estimate chemical abundances in star-forming galaxies from these infrared emission lines. One of the things that they obtain is that there are some small deviations when you compare optical and infrared emission lines. Indeed, there are many errors that you propagate due to the emission lines measurement. But when you check the nitrogen over oxygen ratio, which again, I told you before, is a really important parameter in the study of the chemical content of the gas, you see that there are some deviations that cannot be explained or attributed due to the standard errors of the emission lines and the propagated errors. Moreover, Pérez et al., which also analyzed the nitrogen over oxygen ratio from infrared emission lines, found that there are discrepancies in the nitrogen over oxygen ratio when you compare optical and infrared measurements. Moreover, moving to AENs, Luis et al. In 2022 followed the same kind of analysis, now also introducing AENs. The calibration to estimate the nitrogen over oxygen ratio in AENs was performed by my PhD supervisor Enrique Montero and by myself. What we obtained so far is that indeed we found the same discrepancies that has been reported for star-forming galaxies. However, there are no signs for the oxygen content in AENs from infrared emission lines. So our next step was to upgrade the code that Juan Antonio has been using to estimate the chemical content from star-forming galaxies for AENs. But here we have more troubles than in the case of the optical range. First of all, this is the sample that I will show you here. Mainly we have CIFRs, also we have some ultraluminous infrared galaxies, and also we have few liners. But that's the best thing that we can compile from the literature. Now to this sample, lately I will show you that we have added some galaxies from the IDEO sample that Antonio has been working to. So we have increasing slightly the number of galaxies. Why are we so sure that we have AENs? Because here we can only perform this kind of diagnostic diagram, but you can see that our models of AENs doesn't match at all with the sample. So you can blame me like, no, those are not AENs, they are contaminated by star formation. Well, one of the key signatures of AENs in the infrared range is neon 5 emission lines. Neon 5 emission lines are characteristic of AENs because the amount of energy that you need to ionize neon at such a level can only be reached by AENs. And indeed, our samples show characteristic neon 5 emission lines for all the galaxies. The changes that need to be introduced when you account for AEN or star-forming galaxies are, first of all, higher unique species. The radiation field of AEMs is stronger, so you reach higher ionization states in these elements. And therefore, you need to account for them. Because in the optical range, you cannot measure oxygen 4, but you can do that in the infrared range. If you are not accounting for oxygen 4, then you are not accounting for a significant part of the oxygen ionized, and therefore you are underestimating the oxygen content. But it's not so ideal because we have problems. The main problem is that while infrared emission lines do not depend on the electronic temperature, they strongly depend on the density, because the critical densities are quite below the optical critical densities. Therefore, if you are in a high density regime, the emissivity of these lines is decreasing, and emissivity from diffuse ionized gas is enhancing because it goes to the square of the density. And therefore, you will be accounting at the same time for emissivity from the nuclear part, which will be related to the Nebular region, but also from emissivity from the diffuse ionized gas. And hence, you are contaminating and diluting your estimations of the infrared emission lines. But with our sample, we assure that these contaminations are not so important, and indeed, we just cut the set of emission lines that we can introduce in order to account for this difference in the gas density that we found in the Nebular region. What do we obtain? We obtain again that there is a wide spread range of metallicities for AEMs. Moreover, in this sample, in the infrared range, we do not find any AEM that has, let's say, suprasolar metallicity or even solar metallicity. Just these two here, accounting for the errors, could be solar AEMs. But contrary to the reports that have been doing from optical emission lines, we do not obtain such high metallicity regimes for AEMs. But the problem is bigger, because when we compare infrared and optical estimations, we see a completely different picture. Indeed, not only the nitrogen over oxygen ratio deviates from the optical estimation, as has been reported by many authors, among them Juan Antonio, but also the oxygen ratio deviates when we compare infrared and optical estimations. We try to analyze why we obtain such a result. We try to check if any physical condition of the ISM is driving these discrepancies. So, first of all, we check if the density of the gas is driving discrepancy. As I told you before, density plays a major role in the emissivity of infrared lines. However, the discrepancies that we found, for instance, for the nitrogen over oxygen ratio, do not correlate at all with the density of the gas as has been estimated, neither from optical or infrared emission lines. Secondly, we analyze if the ionization field could be explaining these discrepancies. But again, we do not see a correlation at all between the ionization field and the discrepancies that we found for the nitrogen over oxygen ratio. So discarding these two possibilities, the last possibility that remains, and we couldn't check at all, is that maybe with infrared data, as infrared doesn't depend on the electronic temperature, most cooler regions can be also emitting and being detected in the infrared range, while they cannot be detected in the optical range. And therefore, we are also analyzing at the same time cooler regions that are escaping from the optical observation. Why they deviate from the behavior? Maybe those regions that are clamps of temperature of lower temperature have deviations too in the chemical abundances, leading to a non-homogeneous chemical content of the gas. But again, we don't for sure. This possibility needs to be tested in better data, such as, for instance, the James Webb data. So, which are the next steps that we can expect from this work? Well, as I told you before, nitrogen over oxygen is extremely important, but sadly, there is not going to be far infrared data for the nearby universe. So somehow we need to come up with different approaches in order to infer the evolutionary stages of the metals. In this case, we are extending our sample using IDEOS, and again, we are going to be using star-forming galaxies and AEMs with the same methodology to keep star-forming galaxies as our control sample, trying to reproduce what has been reported in the literature, and then seeing what's going on with AEMs, if they deviate from the behavior or not. And this is, with I would say in Spanish, fresh fish from this very morning, La Lonja. We just been working with the IDEOS sample, and this morning I was checking at the sulfur content of these gases, and this is somehow also puzzling because sulfur is also a primary element, and it hasn't oxygen has a secondary channel production. So therefore, sulfur and oxygen are producing in the same rate from the massive stars. Therefore, the sulfur over oxygen ratio should remain constant, even though accounting for depletion, oxygen can be depleted into dust more often than sulfur can explain some deviations. But what we found is that although there are these deviations in the metal poor regime and the high metal regime, in AENs we found that these deviations are more common than in star-forming galaxies. And again, if we check what has been doing in the literature, mainly for star-forming galaxies, we see that indeed there are some deviations in the sulfur over oxygen ratio. So somehow also far-infrared emission lines are showing us that the deviation from the sulfur over oxygen ratio are also enhanced when we use infrared emission lines. The problem is, would you trust infrared emission lines? Would you trust optical emission lines? This is up to you. I mean, there is no single criteria to say we rely only on optical emission lines or we rely only on infrared emission lines. Right now, with the current data that we have, we obtain different results for infrared and optical emission lines. So yeah, you have two measurements of the chemical abundant content. I mean, it's not ideal in science to obtain two different results, but that's the problem when you have two different observations. It will happen. So we need to be prepared for this in science. I mean, not everything is ideal. And another line of work is the wide range of metallicities. Many authors claim that AENs should expect to have higher metal content. On the other hand, we are obtaining that AENs can have a widespread range of metallicities, presenting AENs low metal content in the NLR region. And this came as a last iteration with an excellent kind referee that suggests us that maybe liners that are most of the majority of our sample in the Palomar survey were not the AENs. Although we showed them that we have radio compact observations and X-ray emissions characteristic of AENs that are indeed confirming that our sample is mainly made by AENs. But again, okay, let's check with a sample of liners by Public Tutorial 2016, where they just measure liners with that has a compact radio source, an X-ray emission characteristic of an AEN. Therefore, they are AENs. There are no other sources that I came up that can explain the same features and behaving like an AEN when you see the optical emission lines. And again, our analysis shows that indeed there is a wide range of metallicities. Not all the liners are expected to be here in the high metallicity regime. There are a wide range of metallicities. So maybe if we account for different natures for liners, let's say the spectral energy distribution is different from what is expected, maybe we can explain these differences. This is an ongoing work that we are doing right now with many data. We are analyzing issues in order to check also the metallicity gradient and how these different models accounting for post-AGB stars. Some authors claim that post-AGB stars, really hot evolved massive stars can explain the same emission that we expect in low luminosity AENs. Even an AEN with an efficiency in a creation can change the accretion disk, and at some point you expect to have not the normal gradient of the material accreting to the gas due to losing energy, but also maybe at some point the disk is truncated and you expect to have advective outflows moving those masses of gas with higher temperature, and then this enhance the radiation field to be lower and the mechanical energy output from the jet will be higher. So indeed we account for that too. So far, our preliminary result shows that mainly none of these different spectral energy distributions introduce a significant change in the chemical content. They introduce a change in the ionization field. In other words, the ionization strength is different, which is also expected because we are accounting from different sources of ionization. And lately, the BPT diagrams. And this is like throwing a stone to my own roof because I don't know if the expression in English, I'm sorry, but that's the translation that I came up. Well, in that, because this is the main classification source that we use, and the main classification source that many people working in gases use. The problem is that I showed you that the nitrogen over oxygen ratio shows a wide variety of values for AENs, and also the sulfur over oxygen ratio. Therefore, these two diagrams, which are the most common use, depends on the nitrogen over oxygen ratio and on the sulfur over oxygen content. Therefore, maybe we are biased. Maybe if we just check into these regions and we assume that they have a solar value average for these two chemical quantities, we are mixing some of the AENs in this spectral classification. This is the ongoing work that has been doing, for instance, when searching for AENs in dwarf galaxies. They expect them to be in different parts of the diagnostic diagrams. The key point from my point of view is that this diagram is metal dependent. You are assuming somehow, if you don't have that information, which is the metal content of the gas that you expect for AEM or for a star-forming galaxy. And therefore, you're mixing extreme objects that have, for instance, enhanced nitrogen oxygen ratio, that could be a star-forming galaxy, relying on the silver category, or on the other hand, you have silver category with really low nitrogen oxygen ratio that can fall in the star-forming category. So therefore, be warning, they are really useful because it's a powerful tool that we can apply really easily, because those emission lines are easily detected in the optical range, but they are strongly dependent on the metallicity. So you have a technique like HII-CHI-MISTRY that I did before, then you can measure these quantities, don't have a problem at all with that, and you say, okay, I will classify the galaxy, but I know for sure that the nitrogen oxygen ratio is things like that. So if they follow in a different category, maybe you can explain that by that very same nitrogen oxygen ratio, and check with a model, a simple model, that indeed with that chemical abundance ratio, you can just cover a different part of the ET diagram. So my conclusions, my takeaway messages is that HII-CHI-MISTRY, both for optical and infrared range, allow us to estimate not only the oxygen content and the ionization strength field, but also the nitrogen over oxygen ratio. And you can do that for optical and infrared emission lines following the same methodology. Moreover, if you want to run your own photoionization models, because you don't rely in cloudy, and you say, I want to run shock models, I want to run another photoionization code or my own photoionization code, you can just generate your own grid of models and you can use them as the grid of models for the code. So, I mean, we provide you default grids, but if you want to test our methodology with other models, you are free to do that and check the results. It will be amazing. This methodology can be applied for AEM and star-forming galaxies. This means that you can have a heterogeneous sample of galaxies and you can apply the same methodology to all of them. You don't need to check for different calibrations, one calibration from this paper, one calibration from this other paper. We do not care about the picture, we do not care about how the measurements of the emission lines were done. No, you can just follow the same methodology. And it's consistent with all the methodologies that I told you before, the three methodologies. Thirdly, the metallicity that we obtain from the narrow line region tend to be slightly higher in AENs than in star-forming galaxies, but tend to be. This doesn't mean that all AENs have higher metallicities than star-forming galaxies. Indeed, I show you that there are some AENs that have even lower metallicities than star-forming galaxies for the very same mass metallicity, for the very same stellar mass value. And we have also performed a study of the infrared emission lines showing that there are some deviations when you match the infrared emission lines with the the infrared estimations of chemical abundances with the optical estimations of these same abundances, which are slightly in the oxygen content, but they are really high in the nitrogen over oxygen ratio. And again, these estimations of the infrared emission lines, which I tell you again, we don't know if they are better or not than the optical estimations, they are just our estimations from infrared emission lines, so that most of the AENs do not have suprasolar values. They are mainly solar and subsolar metal rich galaxies. And spoiler alert, in the coming weeks, I hope, we will be releasing the upgrade for the code to perform the same work for working with ultraviolet emission lines. Again, it's the same methodology. We just need to account now for the ultraviolet emission lines, which are extremely useful, especially at high resolution, because you can measure these emission lines easily. And the work has been already done for star-forming galaxies. If you have a sample of them and you want to check how the code works, but in the next few days, for AEMs will also be released. That's all. Thank you for your attention. Open, of course, to any question that you have.
Thank you very much, Borja. Perfect timing. Questions? Antonio?
So regarding this discrepancy between the optical and the infrared lines, what about the extinction? Because
the extinction,
know that in the narrow line regions,
yes,
many silvers have that.
Yeah.
So maybe in the optical you are seeing the you are biased to the region with less depth, and the infrared you see everything.
Yeah, I totally agree. You cannot perform that study because most of our optical data, which came from arcade data, were already running corrected. So we don't have a reliable source of the content of the dust. But this work from, well, I'm not so sure if pressing F5 will make the presentation to go to the first slide of this very same slide. I'm afraid. Well, this work from Luigi Spinelli et al. 2022, they performed analysis of the data, and they found that there is no correlation with the data. So these three scenarios that have been tested are the three main scenarios proposed by them in 2021. None of them seems to explain the discrepancy, at least in aliens, which is where the test has been performed. Maybe in Star-forming galaxies, once we have a large sample of galaxies compared to those that we already have in optical, we can say that maybe these samples that we are working this many years are just biased towards this result, and there indeed is just some outliers in the distribution. But right now, there are no correlation with any of these properties and the discrepancies.
Mohammed?
So thank you. That was really interesting. I'm not too familiar with spectroscopic surveys like in ALMA, but what is it, fiber or slit?
Slit.
It's a slit. So then, and the slit sizes are fixed for all the galaxies, I guess. For all the galaxies that are observed.
Yes.
So what I want to get at is that the AGN emission we expect is at the center of the galaxy, but then if the slit and like if the galaxies cover a huge size range, like from high redshift to low redshift, or big and small, and massive and not massive, and so on.
Yes.
Then effectively, if the slit size is fixed, then this can also effectively remove or add too much noise to the emission that you expect only from the center of the galaxy.
Yes, I totally agree. The thing is that the Palomar survey, yes, it has a magnitude limit, and all the galaxies that are in the survey, the distance can be measured in megaparsecs. And mainly, the largest region that you can measure in this sample is like up to 800 parsecs, even less.
Okay.
So we are really focused on the nuclear region. Yes, okay. That's the point of using that survey. We are only taking into account the nuclear emission. We are removing contamination for the EM.
It's a nearby galaxy.
Really nearby.
Yeah.
No, 0.1 residual nearby galaxies for
Okay. Yeah, I have that number. Okay, thank you.
Thank you very nice talk. I was going to ask also about the aperture on the spectra, because one of the possibilities that you mentioned to explain the discrepancy was that there are some, if I understood this correctly, there are some star-forming regions which are colder, not necessarily, I mean, emission from colder nebula that is biasing your results.
Yes, I mean, considering the three main ideas that we tested, check the discrepancy, and none of them can explain that, I just came up with the idea that maybe we have a clumsy temperature distribution, and we are seeing also cooler regions. But that's an idea having a beer, and maybe we can check for that. We don't have the data right now.
I think that's a problem in, for example, in planetary nebulae. I think there is some results saying things like that. Like yes, they are missing part of the cold gas emission because the emissivity of the optical lines increases very fastly with temperature. So if you have like 5,000 Kelvin plasma, it's going to be very faint in the optical, but in the infrared, that the emissivity is flat. So you will get the emission from that gas.
Mm-hmm. That's it. Even though I can tell you, I've been working complementary with a partner at IAEA with a planetary nebula, which is called Born Again, because they experience another burst due to gas accreting again to the stars. So it's like a secondary explosion. And what we see is that when we change our optical observations, optical with Megara and with Osiris, yes, and we change it and we take a look at the infrared spectroscopic data, we see that there is an emission that was not, let's say, there in the optical observations because it's really cold. And we are now seeing that because of the aperture, because we have higher aperture, and because it's colder. And infrared will allow us to see that region too. And it's interesting because you see there is a shock ongoing, and then you have that region of cold, like waiting for the shock to be there. So it's kind of amazing that that scenario.
I was wondering, like, how close to the AGN are you measuring with the spectra? Because if it's really close, having a colder region would be less likely. I don't know.
Yeah, but the thing is that the scenario of for instance, the dusty torus, which is surrounding the supermassive black hole, is between the Broadline region and the Northern region, and the dusty torus is also, some of us claim that it's clumpy too. So maybe there is these clumpy regions in the dusty torus that are somehow correlated too, because the dusty torus can also be somehow mixing with the Northern region at some point. So you have clouds with dust there that can be screening also emission. So.
But it's not only a problem of having cold gas, but having stratification.
Yes,
is a problem when you try to do diagnostics with optical lines, because imagine that you have some warm gas and then some hot or colder regions, some inhomogeneities. When you have everything integrated and you try to determine a temperature from there, you're going to be biased because you don't have one temperature, and that's a problem for optical diagnostics, because you don't have access to the temperature of each component. In the infrared, because they are insensitive to temperature, they are much less affected by those problems.
So this is very far from my, well, first of all, thank you. And this is very far from my expertise, but this may very well be a very stupid question, but about the method. Why are you fitting the ratios in 3 steps instead of fitting everything up?
Well, actually,
the first one is the easiest.
Actually, these 2 steps are performing at the same time. The fixing of the oxygen content and the ionization field, mainly because in Star-forming Galaxies you expect a relation between these 2, so you can fit it at the same time. The thing of fixing nitrogen oxygen ratio the first time is because of the relation that I showed you before. We are allowed to vary the nitrogen oxygen ratio in order to check for all the possibilities. But if you measure at the first time the nitrogen oxygen ratio, you just fix all the little models, but you are not assuming a relation between the oxygen content and the nitrogen oxygen ratio. And the thing is that this estimator can be done, for instance, with only nitrogen 2 emission line and oxygen 2, if you have the blue data, or nitrogen 2 and sulfur 2 emission lines. Also, we have released a few weeks ago a paper claiming that be careful with sulfur 2 emission lines due to the big contribution can also affect this estimation. But the thing is that yes, nitrogen oxygen ratio can be estimated with 1-2 estimators, both in optical and infrared range. So it's easier to estimate that, not introducing a bias in the nitrogen oxygen ratio and then looking for these other 2 quantities.
Thanks.
More questions? Maybe among the online audience? If you want to ask something, just unmute yourself. Okay, I have a question. You show that when you study the mass metallicity relations in AGNs, they don't follow the trend. Why do you think this is happening? What can be destroying that correlation, or that correlation is not even present in those targets?
That's a really good question. I wish I had a clear answer. But maybe, like being a bit from Galicia, as to Galicia, I will answer you with another question. And why we should expect only high metal regime for aliens? I mean, there is a possibility aliens are consuming gas in the nuclear region. They are creating the gas from the creation disk. So therefore, they need to have a source, a fueling source. So indeed, you expect to have also inflows of gas. But there is nothing in literature telling us the metal content of those inflows. Even in AGNs, we cannot measure exactly outflows, inflows. We have measurements of outflows for sure, but inflows, I haven't seen a single measurement of an inflow in AGNs. So maybe those inflows of gas are coming from somehow recycled material that the AGN activity, once the star formation has been stopped, or let's say is not so active as in Star-forming Galaxies, we have already a regime of the metals in the gas, which is recycled again, fueling in the AGN, So we expect that, let's say, polluting the metal in the narrow region. That's a possibility, but for sure, I don't know. There are still many open questions, and I think that this kind of studies is important because now we can ask ourselves, okay, is there another driver of the mass metallicity relation which is missing and can explain why these AGNs do not follow that relation at all? That's an open question, and if you have any ideas, any of you, I gladly hear it and take notes for another production.
There are these studies from Nagao, the group from Nagao. They try to study chemical evolution in quasars up to redshift, and their conclusion is that they don't evolve chemically, so they don't change. So you take the spectrum of a quasar in a nearby universe, and then you go to a quasar at redshift 6 or 7. They have some result from a quasar at redshift 7, and they claim that the metal content and therefore the line radius in the quasar spectrum, they are similar. They seem to be like constant. Like when you see a quasar, that galaxy is in a phase that is already chemically mature. That is their.
Yes, I'm aware of those.
So seeing an AGN is a bias on the metallicities of the host.
Maybe because they're using some technique that is strongly dependent on the metallicity, and therefore we are only looking for that. But the thing with that, I am aware of those studies from Nagao and Matsuoka, for instance. They study high-resolution galaxies. The thing is that, okay, you can have that result, but you also need an explanation. In the sense that if you are claiming that the metal content of AGNs doesn't evolve with redshift, you need to explain why a certain redshift, let's say 5 point something, you already have such an amount of metals. I mean, which kind of burst of star formation have occurred in that galaxy already in order to see the presence of those metals at such high redshifts? That's the point. I mean, if you came up with a model and said, yes, for sure, we can produce this large fraction of massive stars within this short period of time, and then just we have this oxygen content already. Then, okay, it's a possibility. But the thing is that they need to be paired. These results are from mainly from the nearby universe. So, yeah, we can have high metal regimes because the galaxy has evolved so well, but you can also have low metal regime, not only because the galaxy is less massive, but also because you have influx of gas, etc. So, yeah, I am aware of the studies, but I mean, you need also to provide a theoretical model to do that.
Related to this, maybe this is a silly question, but in nearby safer galaxies, where you have in those that have nuclear or nuclear star formation gas,
yes,
is the metallicity of this nuclear star formation gas the same as in the Nebular region?
This has been done by some people at Brazil. They are working with manga data. I mean, not so well resolved data, but with spatial resolved data in order to check the metallicity gradient. And in some of them, I will show you here, sorry, the list of references, yes. And to check for those references, Kramer et al. 2021 and Oliveira et al. 2022, they present the studies of metallicity gradients in AGNs. And they found that some of the AGNs kind of break the profile of the gradient. So you expect to have certain metallicity, and then somehow the narrow region is lower than expected. So
if you extrapolate the metallicity gradient from the disk,
yes,
to the center,
you follow the gradient. You have all the H2 regions. So you have a robust technique to the H2 regions. You measure it with the Barrel method. You have exact determination of the chemical abundances for the H2 regions. So you check, okay, this is the trend. I will follow the trend. And when you check the metallicity in the liner, some of them within the errors rely in that expected value, and some of them deviate from that. So yeah, maybe, I don't know, maybe the gas doesn't need to be accreted from the disk profile itself. It would have an accretion directly from other sources. It's really complex. I mean, it also involves models of inflow gas, some models, and yeah, it's an ongoing work, all of this.
Okay. There are no more questions. Thanks again. Borja. Thank you very much, and apologies for the technical problems again.
Gracias, Juan.
Hasta luego, gracias.
Hasta
Hola Pepe, Enrique, ¿habéis oído bien la charla?
Muy bien.
Sí, se ha oído bien.
Buenas, ¿qué tal?
Si estáis hablando, no os oigo.
Ha estado muy bien. Ha oído perfecto.
Estupendo, gracias.
Venga, hasta la próxima.
Pero la cosa es que esto
Chao, chao.
se abre el bloque con el óptico, básicamente todas las acciones para el experimento, entonces lo más cuando tú vas a el perro porque tienes este diseño que vas a ver y de verdad es de alguna manera la estructura de y eso se aplica también un poco contra el trabajo,